All right, so when we're talking about rate of reaction, we also need to be able to represent energy profiles, so changes in energy that happen as a reaction occurs. So reactions can be either endothermic or exothermic, and you need to be able to represent these in a graph. So that means that they don't have enough energy to have the new molecules forming. So let's go and have a look at what this graph's telling us. This is the energy that we are starting with. So this green line tells us how much energy is in the reaction vessel. So if we have a look at this graph, we can see that it has this bump that it has to get over. So this part here, we can see there's a blue line underneath here. That tells us where the reaction is starting. So that's about where we're starting. And then this here tells us that how much energy we're going to finish with. So if we take a look at this, we've got to get over this bump to get to our products. So this is our reactants here. We've got a bump to get over to get to our products. That's called the energy of activation. So that's the energy required to have successful collisions. So let's raise the energy to that energy of activation. So still we're at where the product should the product energy is just about, so let's raise a little bit more. Okay, so that's our product energy. We can see that we're getting increased number of collisions, so they're hitting each other more frequently, but still not with enough energy. So let's raise it a little bit higher to that bump now. Nearly. Okay, we've passed the energy of activation. So now as they hit each other, if we hit in the right orientation, we should be able to form this AB. So we can see now we're getting some AB formed because it's hit in the right orientation. All right, so if we think about what else we could do, so we've increased the temperature and that's increased the number of collisions or frequency of collisions. We could also increase the frequency of collisions by increasing the concentration. So let's increase the concentration of this B. So I'm adding more B in there. Alright, so we are now having more and more collisions. And I'm also going to increase the amount of A. So you can see now we're having a lot more collisions, and the amount of the product, so the amount of the yellow and the purple combining, is greater. So we're getting more successful collisions to form that AB. Okay, so this graph over here that we've been talking about, this is an example of an endothermic reaction. So we can see here that the energy that we started with is lower than the energy we finished with. So the energy difference in the reaction is greater, so it's needed to take energy from the surroundings for this to occur, and so therefore it's an endothermic reaction. That also means that the solution is so the surroundings are going to get colder. Okay, so let's take a look at this exothermic graph now, and we can see here that the energy that we've started off with is greater than the energy that we finished with. So as a result, we're going to see energy released to the surroundings and the container getting hotter. But let's have a look at how this reaction takes place. So similarly, we can see that we have this activation bump to get over. So we're going to start with it lower, and I'm going to add some A. I'm adding a fairly large concentration of A this time because we want this reaction to get moving. Alright. I'm also so nothing's happening yet, obviously, because we've only got one type of molecule in here. So let's add some of this. So we need to hit the activation energy. So let's get that going. So we hit the activation energy, obviously increase concentration, and we can see here that we're forming the products. The important thing to note is what's going on here in this graph, and that energy is being released. Okay, so let's have a look at in a bar graph form, and we can see that we've just about hit equilibrium because the amount of products are forming at about the same rate that we're getting the reactants forming again. So we can see here that we've got these graphs where we're getting a fairly steady stream of both forming. So let's take a look at these energy profile graphs. So what we can see here is that we've got potential energy on one axis and time on the other. So we're talking about any period of time, but the period of time that it takes for the reaction to take place. Okay, so let's take a look at these energy profile diagrams. If we take a look at the first one, we can see that the reactants starts off at a lower energy, than the products. So what we can see is that the products are higher in energy than the reactants are, therefore they're positive. So the enthalpy is positive because it's increased. And that's increased because we've taken in energy from the surroundings. So energy's had to be used in this, but it's come from the surroundings. That means that the temperature, or delta T, is negative because we've taken in that energy or temperature from the surroundings and the solution has now gotten cold. We can also see with both of these diagrams that there is an activation energy required. So we can see down low to the bump in both diagrams, so from here where the reactants are to the bump, there's energy required for this reaction to occur, and that's called the activation energy. And note that in both diagrams we've got here a lower bump where a catalyst has been used. So all a catalyst does is lowers the activation energy. So it doesn't change the delta H or the delta T. It just lowers the activation energy, or the amount of energy required for the reaction to occur. Right, so in the endothermic one, we can see that the products have a much higher energy, or a higher energy, not necessarily much higher, but a higher energy than the reactants. So on the other side, we've got our exothermic, and we can see here that we've got the reactants having a higher energy than the products. So the delta H is negative because we've lost that. But we've lost it in the form of temperature to the surroundings, so delta T is positive. So let's recap what this means. In an exothermic reaction, we have the temperature of the surroundings increasing because heat's released, and our delta H is negative. In our endothermic reaction, the temperature decreases because heat needs to be absorbed and the surroundings become colder, and the energy of the products is greater than the energy of reactants.